So the idea here is to use a Sphero Mini not as a kid's toy, but as a Bluetooth remote sensor. Take it out of the shell and use the IMU, the gyroscope, the accelerometer, use all the sensors in there. So here's the pendulum experiment. Sensor cup, drop it into the bottom. Here's a pendulum. Here's what this looks like. Here's the program SDK with a bunch of stuff. Here's programs, my programs. These are things I've written. Here's this program, which is called Generic Sensor Data Acquisition. It's a non-program. It just turns the light on, turns the stability off, and sets it to not run. It'll find it, it'll turn it on, and I'll turn the light on over there. So we'll start it going now. Start it running and it'll start data logging. I'll turn over here and start the pendulum swinging. Oops, wobble. Sorry, wobbly beginning. So a little bit of air resistance there to damp it out. There, it's pretty much stopped, so I'll stop it running. And then we can look at the sensor data. Orientation is this one here, and Y, the Z is the only one that's interesting. So this is 1G downward, and if I show the rest of the data then and expand the scale, you can see the sinusoidal variation on top of that all the way across. You can download the CSV data, and it downloads it to an Excel file. So here's the pendulum bob turned into the classic swing bucket of water on the end of a string, fast enough to keep the water in the bucket. So start off swinging it slowly, faster and faster and faster and faster and faster, and then slow down. So the accelerometer here is reading the tension in the string. That tension is 1G to begin with, the mass of the object against the string. As I start to speed up, the tension gets greater at the bottom of the loop and less at the top of the loop, and oscillates back and forth, top and bottom, top and bottom. Finally, as it slows down, then we eventually get to the point at the bottom, at the top of the loop where the tension goes to zero. It's weightless there, the tension goes to zero. And here we look at the kinematics of a rolling ball, been hollowed out and sensor put inside. Ball rolls down, the ramp accelerates up and then slows down due to friction. Here's the angular velocity data. Or you can take that sensor out of the rolling ball, put it on a platen to use it as a rotary sensor for all kinds of experiments. The Woods machine experiment, the angular momentum experiment that we do in Physics 111. Mount the sensor here, and there's a pulley. You can pull on it and spin up some objects and measure their angular momentum change. You can also do a angular collision experiment. We'll use this now to do a completely inelastic angular collision. Sum of the initial angular momenta is equal to the sum of the final angular momentum. The spool which we're going to drop on top of the rotating platform has no angular velocity at all, so no angular momentum. So the I platen omega naught is equal to the sum of the two objects which are going to stick together and have a final velocity, angular velocity omega f. If there's no friction, then the omega before would be one value and jump instantaneously to some final value. There's friction, so it slowly comes down, and at the transition, it takes some transition time. So that's what we'll see in the data. Here's the angular velocity of the platen before, during, and after the collision. Comes down due to friction, makes a transition, and then continues with the combined angular momenta of the two objects. Good agreement with theory. So here's some salad spinner physics. Take the sensor, put it inside a salad spinner, and spin it. And here's what the data looks like. We use the data from two sensors, the accelerometer to read the radial acceleration and the gyroscope to get the angular velocity. And if you plot that, you see radial acceleration goes like r omega squared. It goes like omega squared as you expect.
So, the Sphero Mini, not just for kids anymore, a Bluetooth sensor board for at-home learning physics labs.